Welcome to Brain Vision.
So L is equal to 1 nanometer, which is 10 to the minus 9 meters. And so we'll begin with the probabilities. So for n equals to 1, the probability is just the square of the wave function integrated. And in this case, from 0.15 nanometers to 0.35. And we get for the integral the following result. And note that here L is also in nanometers already. So we can just simply substitute in the endpoints, which are already in nanometers, and our units are going to cancel, units of length. So we get 0.200 as our probability. So right here, you'll notice that the units went away because 0.350 was divided by L. Right here, X over L had X and L had the same units of nanometers, nanometers over nanometers, and the same is true right here for X over L. So those units went away. Now we continue on and we do the same for n equals to 2. And it's the same here for L and the endpoints of the integration for the units. Let me move this back up a little just so we can see that. Now we come to the energies. So we see actually the probability for n equals 1 was 0.200. For n equals 2, it was 0.351, so it's a bit higher. Now for the first energy, the ground state, we have h squared over 8 ml squared. When you put in the numbers, you have Planck's constant squared over 8 times the mass of the electron times 1 nanometer squared, converted to meters, though, because of SI units. And we get an energy in joules, which is, of course, the SI unit for energy. And we'll want to convert that to electron volts. It's just more convenient for energy to work in electron volts on this scale. And we have 0.377 electron volts. Now, to get E2, we don't have to do this much calculation. Really, if we know the equation for a particle's energy, if they're a particle in a box, we can just say 2 squared times E1. And we get 4 times E1, and that's 0.377 electron volts times 4. So that just gives us 1 times, or 1.51 electron volts.